Hello. After knowing what is Fourier series, evaluation of Fourier coefficients, let us see the important condition that is put forward for a function for its represented in terms of Fourier series. And these conditions are defined by a theorem known as Dirichlet's theorem. So here we will discuss the Dirichlet theorem and graphical representation. As an example, we will discuss the graphical representation of even and odd functions. Let us discuss Dirichlet theorem. So, in order to represent a Fourier series on a graph, we have to discuss the convergency of a function. If function fx represented by Fourier series is to be drawn graphically, then we have to test the convergency of the function fx. In order to test the convergency, that where the function fx is convergent, we have to define the continuity of the function. In other words, we have to define where the function is discontinued, whether the function possesses discontinuity. What is discontinuity? Discontinuity is the situation that arises when a function suffers a finite jump. What is finite jump? Suppose we have a function fx, that means it is a function of variable x. Then for a particular value of variable x, say x0, if discontinuity occurs, function becomes discontinued for x equal to x0, then it is said to be a finite jump at x equal to x0. And if it is a finite jump at x equal to x0, there exists two limiting values of fx at x equal to x0. Interesting, isn't it? For a single value of variable, that is x0, since there is a finite jump, we came across two values of a function fx. Now, how these two values exist? Let us see very first one, that we are approaching the discontinuity, the finite jump at x0 from a right hand side on the graph. Now, if point A is towards the right side of the discontinuity, that means point A has some greater value on the x-axis. Say point A is at x, that is equal to x0 plus delta x. In that case, we can express fx0, that means value of function f at x0, in terms of variable x0 plus delta x by using a function limit, such that fx0 equal to limit delta x tend to 0 of fx0 plus delta x, and let us call this as equal to f x0 plus, since it is from the right hand side, so from the greater side of variable x0. So the same situation is represented by a graph in this next slide. As we have discussed, there is a finite jump at x equal to x0. So when function fx starts at x equal to 0, it was smoothly running, and at x equal to x0 there is a finite jump towards upper side. We considered here in this figure the 2 points, where point A is towards right side of the jump, that is right side of the point x equal to x0, and since it is towards right side, it has some value greater than x0, say x0 plus delta x, and the value of function f at x0 can be expressed in terms of x0 plus delta x as fx0 equal to limit delta x tend to 0 fx0 plus delta x, and let us denote it by fx0 plus at point A. So this was approach from the right hand side. Now consider a point B towards left side of the jump x equal to x0. Then it has some lower value. Let us denote it by x0 minus delta x. So as it is indicated by point B on the figure. Now function fx0 can be represented in terms of its value at x0 minus delta x by using function limit as fx0 equal to limit delta x tends to 0 fx0 minus delta x. So within limit, when delta x tends to 0, fx0 minus delta x will give rise to fx0, and let us call it as fx0 minus, since it is from the lower side of x equal to x0. In this way, at x equal to x0, we came across the true values of the function. Towards upper side it is fx0 plus, and towards lower side it is fx0 minus. And it is important to note that fx0 plus is not equal to fx0 minus. When this inequality shown by equation 1, that is fx0 plus is not equal to fx0 minus, is satisfied by function fx, it is known as a discontinuous function. Interesting, isn't it? We are going to define continuity, and we defined discontinuity. Of course, since it is important for a function to be represented by a Fourier series. In this way, discontinuity occurs at x equal to x0, where the inequality shown by equation 1 holds. In this situation, the Dirichlet theorem, very important theorem, deciding or guiding for a function to be represented by a Fourier series, holds. Now what is this Dirichlet theorem. Up till now we have discussed that to hold Dirichlet theorem or to satisfy the Dirichlet theorem by a function fx, the function must be discontinuous. And when a function is discontinuous at a point, it has two values, and these two values are unequal. And when inequality exists for these two values at a point or at a finite jump, then Dirichlet theorem holds. And what is this Dirichlet theorem is? According to Dirichlet theorem, every single valued bounded function fx has only finite number of finite discontinuities and only finite number of extreme values, maxima and minima. And such a function can be expanded or represented in terms of a Fourier series. So, in other words, Dirichlet theorem explains which function can be represented in terms of Fourier series. And according to Dirichlet theorem, a function which has finite discontinuities and finite values of maxima and minima can only be represented by a Fourier series. Such a function which has finite discontinuities with finite values of maxima and minima is known as piecewise regular or a smooth function. In other words, if a function is discontinued and it has finite discontinuities with finite values of maxima and minima, it is known as a smooth function or piecewise regular function, and it is represented by a Fourier series. So this is what Dirichlet theorem says. We have the expression for Fourier series as fx equal to a0 plus summation n equal to 1 to infinity an cos nx plus summation n equal to 1 to infinity bn sin nx, and is valid only for those functions which are regular or piecewise regular in the interval minus pi to plus pi with period 2 pi. So this is what we know from the Dirichlet theorem, that a Fourier series given by the equation is valid within the period minus pi to plus pi, that is with period 2 pi, only for the regular or piecewise regular or smooth functions, that means which has finite discontinuities with finite values of maxima and minima. And these conditions, that a function must have finite discontinuities along with finite number of extreme values, maxima and minima, are called as Dirichlet conditions. In other words, Dirichlet theorem says that a function fx, in order to represent a function fx in terms of a Fourier series, the function must possess a discontinuity, Moreover, these discontinuities must be finite, and since there are discontinuities, so there will be values of maxima and minima, and again these values of maxima and minima should be finite. If this exists, then and then only the function is represented by a Fourier series. So this is about the Dirichlet theorem. After knowing Dirichlet theorem, let us try and represent the simple functions, that is even and odd functions. As we already know that if fx is even, we came across a Fourier series as a series of cosines only, and we call it as cosine series. And if fx is odd function, then we came across a Fourier series with sine terms only, which is known as a sine series. So let us discuss how the even series and odd series can be represented graphically. Let us evaluate the even series first. For a even function, fx is equal to f of minus x. So this is the condition that changing the variable value of sign of variable x from positive to negative does not change the value of function. So fx equal to f of minus x. And we know that in terms of Fourier series, fx can be represented as a0 plus summation an cos nx plus summation bn sin nx, where cosine and sine functions are infinite in number. Now, what is value of Fourier coefficient a0? It is 1 by 2 pi minus pi to plus pi fx dx. Now let us divide the interval minus pi to pi into two different halves, that is minus pi to 0 and 0 to pi. So in this way we have the next term 1 by 2 pi in bracket minus pi to 0 integration minus pi to 0 fx dx plus 0 to pi fx dx. So integration minus pi to 0, let us alternate the lower and upper limit of the integration. So integral becomes negative. So it is minus 0 to minus pi fx dx in the next term, where 0 to pi fx dx as it is. If we replace x by minus x and minus pi by plus pi, so minus sign becomes plus. Okay, so we have 1 by 2 pi 0 to pi fx dx plus 0 to pi f of minus x dx. But since function fx is considered as even function, f of minus x is equal to fx. So therefore we have 1 by 2 pi in bracket 0 to pi fx dx plus 0 to pi integration 0 to pi fx dx. That is 2 into integration 0 to pi fx dx multiplied by 1 by 2 pi. Finally, a0 is equal to 1 by pi 0 to pi fx dx. This is how a0 is evaluated for even function fx. Let us evaluate value of the Fourier coefficient an. We know that an has a value given by 1 by pi minus pi to pi fx cos nx dx. Again, the interval minus pi to pi is divided into two separate intervals, minus pi to 0 and 0 to pi. After that, the limits minus pi to 0 are converted to 0 to minus pi and integral becomes negative. In the next step, x is replaced by minus x. For the second integral only, x is replaced by minus x and nx is replaced by minus nx, and so that our upper limit becomes plus pi and integral becomes positive. But as fx equal to minus f of minus x is equal to fx and cos of minus nx equal to cos nx, both are even. So we have f of minus x into cos of minus nx equal to fx cos nx. So in this way, in bracket we have 0 to pi fx cos nx dx plus 0 to pi fx cos nx dx. So 2 into 0 to pi fx cos nx dx. And in this way, an evaluate as 2 by pi integration 0 to pi fx cos nx dx. So this is about evaluation of an explained in this slide. Now, the third Fourier coefficient Bn. Here again the same we have made. We know that Bn is 1 by pi integration minus pi to pi fx sin nx dx. Here also we divide it into two intervals. Minus pi to pi is divided into two intervals, minus pi to 0 and 0 to pi. Upper and lower limits of the integral with minus integration from minus pi to 0 are exchanged. So it is altered and it becomes integration 0 to minus pi with negative signs. So this is the second integral shown in the third step on this slide. Then x is changed to minus x for the second term, and in this way it becomes integration 0 to pi. So upper limit change from minus pi to plus pi and integral becomes positive. But f of minus x is equal to fx and sin minus x equal to minus sin nx. So therefore the product f of minus x sin nx is equal to minus fx sin nx. And in this way we have two integrals, two identical integrals with opposite signs in the square bracket. That is 0 to pi fx sin nx dx minus integration 0 to pi fx sin nx dx cancelled out and bracket value becomes 0, so that Bn vanishes to 0. Thus only a0 and an survives while Bn reduces to 0. So in Fourier series we have two terms only, since Bn, the third term, Bn is 0, the third term vanishes. So fx equal to a0 plus summation n equal to 1 to infinity an cos nx will be the series. Here we have to substitute values of a0 and an. So a0 1 by pi 0 to pi fx dx and an 2 by pi integration 0 to pi fx cos nx dx. So Fourier series fx equal to 1 by pi 0 to pi fx dx plus summation n equal to 1 to infinity 2 by pi 0 to pi fx cos nx dx into cos nx. In this way, the series has cosine terms only and it is known as cosine series. Now, how to plot on graph? While plotting on graph, we have to remember this, that since it is an even function, f of minus x is equal to fx. So, fx equal to f of minus x. For example, if f equal to pi, then f of pi is equal to f of minus pi. So, we have plotted here the function within limits minus pi to pi, and we find that when x changes from minus pi to pi, the value of fx on the y-axis is always positive. For f pi it is positive, for pi x equal to pi it is positive, for x equal to minus pi again it is positive. So this is the graphical representation of even function. Now let us find the graphical representation of a Fourier series of odd function. For odd function, f of minus x is equal to minus fx, and let us evaluate the Fourier coefficients one by one. Now we know a0 it is equal to 1 by 2 pi minus pi to pi fx dx. Here again the interval minus pi to pi is divided into two intervals, minus pi to 0 and 0 to pi. Again minus pi to 0 is altered to 0 to minus pi, where the integral becomes negative, as it is represented by the second integral in the third step, in the second step. And now x is replaced by minus x. So f of minus x, so that minus pi is represented by pi and second integral becomes positive. But f of minus x is equal to minus fx, since it is an odd function. So we have in bracket two terms with opposite signs, that is 0 to pi integration 0 to pi fx dx minus integration 0 to pi fx dx. They vanishes and bracket value becomes 0. So a0 becomes 0. So this was evaluation of coefficient a0. Let us evaluate the next coefficient an. Okay. So 1 by pi minus pi to pi fx cos nx dx. So this is the evaluated value of the Fourier coefficient an. Here we will divide interval minus pi to pi into two intervals, minus pi to 0 and 0 to pi. Minus pi to 0 is converted or changed to integration 0 to minus pi by putting negative sign as a second term in the third step. And then x is changed to minus x for fx and cos nx. And upper limit is changed from minus pi to plus pi for the second term in the fourth step, so that second integral becomes positive. But since f of minus x is equal to minus fx and cos of minus nx equal to cos nx, we have f of minus x cos of minus nx as equal to minus fx cos nx. So in square bracket we have two terms with opposite two identical terms with opposite signs, that is 0 to pi fx cos nx dx minus 0 to pi fx cos nx dx. They cancel out and value of square bracket becomes 0, and in this way an also becomes equal to 0. Now what about the third Fourier coefficient Bn? We know it is represented as 1 by pi minus pi to pi fx sin nx dx. So let us divide it into two intervals, and again we are following the same procedure, that is minus pi to 0 is converted to 0 to minus pi and putting the negative sign, and then x is changed to minus x, minus pi upper limit of the second term changed to plus pi with positive sign to the integral. Since f of minus x is equal to minus fx sin of minus nx again equal to minus sin nx, so it is f of minus x sin minus nx, it is equal to fx sin x, and by putting this value we have two identical integrals with same positive sign. So in bracket we have 2 into integration 0 to pi fx sin nx dx. In this way Bn equal to 2 by pi 0 to pi fx sin nx dx. So after evaluation we find that only the Bn exists, Fourier coefficient Bn exists, while a0 and an both becomes 0. Thus the Fourier series is represented as summation n equal to 1 to infinity Bn sin nx, and where we put the value of here Bn, that is 2 by pi 0 to pi fx sin nx dx. In this way we have a Fourier series which has sine terms only, and this is known as sine series. Now how to plot this sine series or odd series of odd function on a graph? For this we have to remember that f of minus pi is equal to minus f pi. So pi becomes negative or x becomes negative, its value becomes negative. So same thing we have done here. For plus pi it has a positive value towards positive side of the y-axis. For negative it is towards the negative side of the y-axis. So thus we can represent the sine series. In this way we obtain the graphical representations of even and odd functions, that is cosine and sine functions respectively. Whole lecture can be summarized as a function which has finite number of finite discontinuities and finite number of maximas and minimas. Such function only can be represented by a Fourier series, and these conditions are called as Dirichlet conditions. So with this we conclude today's lecture. Thank you for listening. Thank you for your patience. Thank you very much.